Good afternoon. My name is Dimitrakopoulos and I will present our work with my colleague Grigoris Kostopoulos and Professor Stelios Georgantzinos on improving the dimensional accuracy of PLA parts produced by fused filament fabrication using Takeuchi design of experiments.
Fused filament fabrication is now a standard tool for low-cost, rapid prototyping in many engineering environments. However, the printed parts often do not perfectly match the nominal CAD dimensions, which can cause problems in assemblies and functional components. Our motivation is to move beyond trial and error tuning and identify robust parameters settings that consistently give good dimensional accuracy. The main aim of this work is to quantify and improve the dimensional accuracy of PLA parts produced on a desktop FFF printer. To do this, we use a Takeuchi L9 design and systematically vary three key process parameters: layer height, printing speed, and extrusion temperature. Based on the experimental results, we want to propose simple, practical guidelines that any user can apply to achieve more accurate PLA prints. We briefly recall how the FFF process works. Thermoplastic filament is fed into a heated nozzle, melted, and deposited layer by layer on the build platform. During cooling, the material screens and residual stresses develop, which can lead to warning and dimensional changes. In this study, we focus on PLA, which is very common, easy to print bio-based polymer used in most desktop 3D printer. Dimensional accuracy is a realistic way. We designed and dedicated calibration parts that combines different geometries: blocks, cylinders, slots, and 40mm bar. We defined 35 linear dimensions grouped in the 6-dimension sets so that we capture error in multi-directions and future types. For each parameter combination, we printed 5 identical specimens and we measured all dimensions against the nominal CAD values using high resolution methodology. Of testing all possible combinations of the 3 parameters, which will require 27 experiments, we use a Takeuchi L9 orthogonal array. The L9 design allows us to study 3 factors at 3 levels each, using only 9 tests, while still being able to estimate the main effects of each factor. Our response variable is the mean absolute dimensional error, and our quality target is smaller the better. We can see the 3 parameters and the ranges we selected. Layer height varies from 0.1 to 0.3 millimeters, covering fine to coarse resolutions. Printing speed ranges from 30 to 70 millimeters per second, and the extrusion temperature is set between 200 220 degrees Celsius. All other settings, such as infill cooling and build orientation, are kept constant so that we isolate the influence of these 3 factors. These slides show the mean absolute dimension error for each of the 9 test parts, average overall measured dimensions. Most parameters combination produce error rates of about 0.08 to 0.12 millimeters, which corresponds roughly to 1% for a 10 millimeters feature. However, one combination test part 9 clearly stands out with a much higher error of about 0.26 millimeters, and this is our worst case. If we group the results by factor levels, we obtain these main effect trends. First, dimensional error increases noticeably as the layer height goes from 0.1 to 0.3 millimeters, so thin layers are beneficial for accuracy. Second, the high printing speed at 70 millimeters per second leads to poorer accuracy compared with 30 and 50. And third, in our experiments, the intermediate temperature to 210 degrees performed the worst, while 220 degrees Celsius gave the lowest average error. To account for both the means performance and the variability, we also evaluated the Takeuchi signal-to-noise ratio with a smaller the better characteristic. The highest SN ratios are obtained for conditions involving 0.1 mm layer height, which means these settings are not only accurate on average but also most robust. The lowest SN against corresponds to test part 9, confirming that this is the least desirable parameters combination. We then performed an analysis of variance to quantify how much each factor contributes to the total variation in dimension error. Layer height is clearly the dominant parameters, accounting for roughly 44% of the variance. Extrusion temperature and printing speed contribute around 19 and 16%, while the remaining variation is attributed to noise and other effects that we did not model explicitly. By combining the information from the main effects plots and then SN analysis, we can propose a simple set of recommended settings. The optimum region is for dimensional accuracy the layer height of 0.1 mm, relatively low printing speed of around 30 millimeters per second, and an extrusion temperature close to 220 Celsius. The combination is suggested for both for future confirmation experiments and as a practical recipe for printing accurate PLA parts. All the experiments indicate that thin layers combined with moderate printing speeds offer the best compromise between dimensional fidelity and build time for PLA FFF. The Takeuchi-based methodology we used here is quite general and can be applied to other materials, geometries, and even other additive manufacturing processes. To calculate this work, applied the Takeuchi L9 design to study how layer height, printing speed, and temperature, extrusion temperature, influence the dimensional accuracy of PLA parts produced by FFF. We found that layer height is the dominant factor, followed by extrusion temperature and speed, and we recommended parameters window of 0.1 mm layer, low to moderate speeds, and nozzle temperature around to 220. Future work will investigate additional parameters, possible interactions between them, and validation of more complex functional components. Thank you very much for your attention, and I will be happy to answer any questions.